to formally talk about the solution process for solving the multiple degree freedom system. And there's two types of the vibration problem that we're going to solve. One is what we call the free vibrations. So that means the multiple degree freedoms without any externally applied force. The second portion will be 1 or 2 lectures hours. Later on, that will be unforced vibrations. Okay. So today's lectures will cover the homework 12. And I wish I can cover as most as possible. And this will be the formally very rigorous and the solution process. And so I will try the strategy for today will be this. On this side, show you the theoretical steps in terms of the symbols. On that side, I'm going to work on one example in numbers. So initially you can compare. Also, in homework 12 and 13, I have written quite a bit Part 1 tutorial information. You can also refer to those things to help you.
That's hard to follow.
And then later on to polish your calculation skills.
Yeah, it's hard to follow.
Yeah, and as long as you have a big concept, the remaining the calculation, just be careful. So I can try to help 2 plus 3 plus 1. So that is a concept, and our goal is to determine the response, x1 and x2, in terms of any given initial conditions. And so here we assume the vibrations is, again, this is the linear harmonic, linear vibration systems, and for each of them, although they are coupled, but their response still in harmonic response. So here the same we assume the solution is in this form, cosine or sine. Basically, we assume the solution is harmonic. Okay. So for harmonic, and that is we did before in chapter 2. We assume for 1 degree freedom that in certain harmonic, and this is a phase angle. Okay. This is the unknown amplitude. Here we have 2 degree freedoms. So in the second one, we assume the same way. Okay. So that is a difference from the chapter 2. In our single degree freedoms, we only assume one form, but in the 2 degree freedom, you simply assume the 2 forms. Okay. The assumption here, a feature is this. Here we assume they are in certain unknown natural frequencies, and with certain unknown the amplitude, with certain unknown phase angle. Okay, and then here for the natural frequencies for this form, we assume using the one symbol. But here you can see the amplitude, they are different. So that means we assume that both amplitude in certain vibration mode, they will have the same the patterns of the vibrations, but with a different magnitude. So that is the meaning of this one. So with this one in mind, we can begin to do the derivations. So how to do it? So basically here we consider we plug in into the assumed solution. So let me rewrite here. Sorry. So here again, here is our textbook notation x1 and x2, and I feel that is a little bit bothersome. So compared to the textbook, I changed into C1, C2. That will be more intuitive than simply indicating a certain unknown coefficient of the vibrations, or I would say amplitude. Okay, so keep this in mind. Then we begin to do the plugging the informations into there. So to plug in, you need to calculate x1, and you need to calculate x1 dot as well, right? Based upon that one, you can easily see that will be minus omega squared times C1 and cosine omega t plus v. Okay, so if you can see this one here. So in a similar way, x double 2, the x2 double dot, the same thing, minus omega squared c2 and cosine something the same. Okay. So with those things, you plug into these equations very carefully, and so maybe from here we can try one example here. is we consider this example. Where is my name? 10, 0, 0, 1, x1 dot, x2 dot, plus 35 minus 5 minus 5, 5, x1, x2 equal to 0, 0. Basically, this is the equation of motion of such a system. Let me draw it here. So M1 equal to 10 and M2 equal to 1. And this is a spring 30, and this is spring 5, and this is a spring 0. Okay. And of course, if I would change this one to non-zero, then these things will be modified a little bit on the stiffness matrix. So for this one, you can exercise to see this is a wall here. Okay. So for this case, our solution is this. We're going to find the free response. Okay, so here we call the free response because this is a free vibrations. The free vibration, that means the force term equal to 0. So that is called the free vibrations. So that's the reason why we call this called the free response. So the solution process is this, we assume. And not actually, it's not assumed, this is true, okay? But here, we assume the solutions, x1t is in harmonic excitations, and using our notation is C1 and cosine omega t plus phi. And x2 equal to C2 cosine omega t plus phi. So with this one, then we can calculate the x1 dot dot equal to minus square x1 and x2 dot dot equal to minus square x2. Okay. Yes.
In your drawing up there, why do we assume that K3 is equal to 0?
Oh, that is for my assignment for my design of this problem. If you don't like, you can just simply remove this one. Okay, and I think the best one, you just in the problem can multiply like this. Okay. So with this one, then we simply plug in and then do the things carefully. Okay, so basically this one, the equation becomes 10, 0, 0, 1. And x1 dot dot is minus omega square x1 minus omega square x2. And I simply plugging into a right positions here, minus. So when I write too much, too quickly, sorry, suppose this should be distinguished, but hopefully you don't mind, I write off too quickly, okay? So, right now from here, you can see, for the two multiplication of these two matrices, I want to do a little bit tricky things. Once you expand it, let me do the scratch of the side. If you expand it, this one basically becomes 10 times minus x. This one basically minus 10 omega squared x1. Okay, and this one, if you expand it, this one multiply with this, and this one multiply with that one, become like this, right? if you expand this matrix, you multiply this row with this column equal to this number, and you multiply with this column with this row with this column become this one, right? Okay, so basically this one can be rewritten like this: minus 10 omega squared 0, 0 minus omega squared and x1, x2. Okay, so basically this is what I need. I simply, okay, so that's what I need. So from here, let me copy the information here. So basically this one becomes, let me copy here, minus 10 omega squared 0, 0 minus omega squared. And then multiply with x1, x2, and plus the same thing here, we copy. Okay. So now this is the manipulations on the matrix. So right now you can see the coefficient, the variables are the two, these vectors, and pre-multiply the two matrices, you can visualize at the coefficients of the parameters. So I can combine the two matrices together. I add it up together. So basically that one is this matrix plus this matrix and multiply x1, x2 equal to 0. Okay, so let me multiply them, add it up together, minus 10 omega squared plus 35 minus 5 minus 5 minus omega squared plus 5. Okay? So right now, again, this one simply in scalar sense, simply just like this: ax plus bx equal to 0, and a and b are simply the two matrices. We can simply using the associate rule to get them together, right? Something like this one. And then for matrix, their addition simply is the element wise. We added up the terms together. And what is this term? This term here is a theoretical descriptions. Compared to our numbers here, what I did is I take the x1, x2, x double derivative, the x2 double derivative into the equation of motions. Then I rearrange something like this one here, okay? So basically this equation will be similar to here. Let me give more explanations. So for this one, right now we have down here, and have you seen, is this one. Let me do the scratch again to remind you what is this. If we have the typical eigenvalue problems, and that is given by ax equal to lambda x. And what we have learned before is this. We can rearrange this one is a minus lambda I times x equal to 0, or vice versa, minus lambda I something like this one. And then, for example, say, so if A equal to A11, A12, A21, A22, and then lambda I for the 2 by 2 matrix basically is lambda 0, 0 lambda, okay? So, for example, here, if we with these numbers, then this equation is like this. A minus lambda I is A11 minus lambda, A12, A21, A22 minus lambda times x1, x2 equal to 0. So here I should put into a values here. Okay. And let me rewrite one more time. So let me reverse the order: minus lambda plus A11 minus lambda plus A22, A12, A21, x1, x2 equal to 0, 0. Right? I simply just swap the two numbers together, right? You compare this form to this. You compare this, the typical eigenvalue problem statement with these equations. So can you see right now, corresponding to our eigenvalue problems lambda, that have the rho plate here. So this is our eigenvalue problems. Can you see it? Okay, so basically this one is our typical eigenvalue problem statement. So if you remember our eigenvalue problems, the first step is to solve for the eigenvalues. How to solve for the eigenvalues? The eigenvalues basically, if you remember, is this. We simply pick this is the matrix and we ask him the determinant of this matrix equal to 0. Right? So that is what we did last time. If you remember, I tried to read. Okay, so basically for our problems, the step 1. Step 2, solve for the eigenvalue problems like this one. So that means here, follow up this one, we need to get its determinant of this matrix minus 10 omega squared plus 35 minus 5 minus 5 minus omega equal to 0. That corresponding is our statement here. The step 2, the first step. Be good? Yes.
To make the algebra a little bit easier, can we just leave lambda in there while we do the calculations? Or
Leave lambda to in where?
can we solve for lambda instead of omega?
Yes, yeah. The rho basically for this case, yes, omega basically is the eigenvalues. Okay, and okay, wait for that one. Let me implement this one. Whatever the form, we have to get the determinant of this value. Okay, so this one basically is the things multiplications of the two terms minus multiplications of the two terms, and that is a 2 by 2 matrices. So that means complete here. Minus 10 omega squared plus 35, and minus omega squared plus 5, and minus 25 equal to 0. So that is this equation, right? And for that equations, be careful and like I said, engineers will have to assuming the perfect, so no mistake in any calculations. This is going to make a mistake here, and even for me, I made a mistake quite often here. So be careful on that one. So this one, once you implement it, and that will be equal to 10 omega to the 4th and minus 85 omega squared and plus 150 equal to 0. This is a polynomial in omega. Okay, so back to your questions, why not we directly use omega rather than lambda, or why not we directly solve for omega, whatever the question is. So that is here. So basically, this is a polynomial in terms of the omega. As long as we can solve for the roots, then omega that numbers is our natural frequencies. Right? Okay, we see how to solve for this one. This is the fourth order polynomial, and couple ways we can do it. So if you like, you can say that is 10, assuming say lambda equal to omega squared, that basically is 10 lambda minus 85 lambda, and plus 150 equal to 0. So basically this is the second degree polynomial. Then the lambda 1, 2, you can see manually is that equation 2a minus b minus plus b squared minus 4ac. Whatever that equation, that is the one we can know, we can solve this manually, okay? So this one we solve for lambda, and that is 2.5 and 6. We have two numbers. And lambda 1, 2, basically that is omega squared 1 and omega squared 2. We have two things. Okay, or otherwise, like your question is this, otherwise we directly solve for the root of the fourth degree polynomial. In MATLAB, you can use this command, roots. And for this one, you place the coefficient found in the descending orders. 10, 0, minus 85, 0, and 150. Once you hit return, you must have the four numbers, okay, and pick the positive, because natural frequency is always positive. The four numbers, two of them are opposite sign, but with the same magnitude, I guarantee. Otherwise, you have made mistakes somewhere before, okay. So that answer your questions? Good, okay. So either way, okay. So for example, you pick up this one, then basically you can see omega 1 equal to squared 0.5, and the unit is right away in this. Assuming assuming here, say this is the 10 kilograms, okay, this is the Newton per meter. If the unit is in certain consistent way like this, then this must be in this, okay. So omega 2 equal to square 6, and that equal to whatever, radian per second. Yes?
Is it ever possible for the solution for omega to be imaginary?
Stand that again.
Is it possible for the solution for omega to be imaginary?
No.
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 Just based on the...
Yeah, it's always, I can guarantee, if you solve for lambda or if you solve for omega squared, it must be positive or 0.
Just based on
no negative.
Just based on the problem set.
Yeah. If you have anything negative coming up, then, or if you have anything imaginary numbers coming here, check your calculation here. This step is very easily that you will make. If everything you come up with from here is not real, not practical, then again, check the calculation here. Okay? So that is step 1. We have found the natural frequencies, which means the eigenvalues. And then the second step is to determine the eigenvectors, which means vibration mode. So here is a theoretical process. Basically, we take the determinant of that matrix, and then here is the formula provided for 2x2 matrix. We solve for the natural frequencies, okay? So now we're going to, we have done this step, so I'm kind of the white out that one. Now we're going to solve for the eigenvectors. This is a step, and then we're going to solve for vibration mode. And vibration mode, in terms of our eigenvalue problems, that is for the eigenvectors. Okay. So the step is this. Let me. Using this equation, let me call it, this is equation 1. Okay. Again, before we solve for the details, how many vibration modes we have? 2. Again, that is a basic concept. Here we have 2 different frequencies. And so here we have 2 natural frequencies. And we have 2 vibration modes. Vibration modes, or we call them modal vectors. We have 2 vectors. So that means for omega equal to the first one, omega 1 equal to 0.5, the associate mode, vibration mode is this, etc. For second vibration, for second natural frequencies, we have the second associate mode. Okay. Each mode associated with each frequencies, you shouldn't misuse. Okay. This one is to use equation 1 to solve. Equation 1 is like this. So let me rewrite here. So that is minus 10 omega squared plus 35 minus 5. Okay, and then using these equations, we simply plug in omega equal to 2.5 square root, or equivalent to say, why not we put the omega, okay, whatever, we just put it here. Okay, using this value plugging here, and that matrix basically is simplified into this. So omega squared is 2.5, so 25 into 10 minus 5 minus 5, and this is omega squared. How much? Omega squared 2.5. Is that right? Okay, after simplification, you plug in omega squared equal to 2.5 into here. And now from here you can see this equation becomes, if we expand it, this represents a 2 set of equation. That means 10x1 minus 5x2 equal to 0, or minus 5x1 plus 2.5x2 equal to 0, right? If you expand it, that representing by the 2 equations, and you can see the 2 equations are dependent. So really, you are not able to solve for a unique value for x1 and x2, but you can solve for their relations. And that relation is what we call the vibration mode. For example, here using this one, for example, let me pick this one. Basically, this one tells us is this. x1, that tell us x2 equal to x1, right? Or otherwise, if you use the second equation that is the same, you can get these relations. This is 2x1. So by using either equations, you can get the same relations. Okay, and that is the essence of the eigenvectors. Eigenvectors, that means there's no unique solution for individual parametric variables, but we know, at most we can know is the relation. The relation, for example, is this. x1, x2 equal to, for example, say, let me pick x1 equal to alpha, then x2 should be 2 alpha, and alpha is arbitrary numbers. This tells us the relation. So that means it's alpha. Let me put the alpha here, 1, 2. So 1, 2, this vector is our vibration mode, or we call the modal vectors. Corresponding to the first natural frequencies, this is called the first vibration mode. Or you can say that is the first modal vector, because that really is a vectors. You good? And someone could ask me, how do we determine alpha? We don't have to. The reason why I will explain that to you later. Okay. So here, the 1, 2, this is the associated vector mode or vibration, the vibration mode corresponding to omega 1. We can repeat the same calculation for omega 2, and we can get the second vibration mode. And we can do this one here quickly. Let me write it up here. For B, and that means for omega equal to omega 2 equal to 6, square 6. So again, right now, let me minus 10 omega squared plus 35. Something like this. So basically here omega equals square 6. Okay. So this number, let me rearrange this one. So omega squared equal to 6. So minus 25. 5 minus 5. 1. Okay, so basically these equations, in a similar way, that becomes minus 25 x1 plus 5, x2 equal to 0, which is 5. Oops. So after implementation, that becomes this. And again, this once we expanded this kind of the matrix representation that representing either two equations, by either one we can get is this x2 equal to 5x1. Let me double check my calculations. I think I made some mistake here, right?
Drop in negative.
Yeah. So here I made a mistake here, right? Okay, so this should be minus 5, so this should be minus 5. Good, thank you.
Also, you should be negative 1. You're putting it to 6.
Yeah, this is negative 1. Sorry, 2 mistakes. Thank you. Okay, so that is this one, so this one. Okay. So therefore, from here you can see the x1 and x2. The relations x1, x2. For example, say we like the x1 equal to say beta. Then this one will be minus 5 beta. So that is beta times 1 and minus 5. And again, from here we obtained the second vibration mode. Okay. To this point, you pretty much overcome the first major half of the solution process. And then with the two things together, we still back to solve for our problems. So we're back to here and look at our notations. So basically here, right now for first vibration omega 1, we have come up with this one. In terms of the symbols, 1 R1, that is similar to our 1, 2, and C1 is certain arbitrary constant, okay? In our textbook, when you read the chapter 5 and chapter 6, this superscript with certain brackets that indicating is for first vibration mode. Okay, that is the notations. Okay, so that indicating, and for second one, then that is the second vibration mode. So this page is a summary of what we have done there for first vibration mode, we have certain the vector. For second one, we have a certain one. And the two vectors shouldn't be the same. Okay, again, if you come up with the same vectors, then double check it with your calculations. Any questions to this step? Are we good? Good, right? Okay. Another note is this. For example, for this model vector 1, 2, and there are so many equivalent expressions, really depends on how you select your alpha. So say, for example, say you can answer the vibration mode, the first mode is 1, 2, or you can give the answer 10, 20. Really depends on how you're going to choose alpha to scale up or scale down. As long as you keep the ratio of the elements the same, then your answer will always be, there's always infinite numbers of the answers for describing a vibration mode. As long as the ratio keep the same. So for example, you can say the first vibration mode is 1, 2. The other students say my first vibration mode is 10, 20. Both of you are the same. You're describing the same answers. You good? Okay. Yes.
So how does a
Modal vectors.
change when you talk about a bigger system, like if you had 3-vector matrix or something?
Yes. Yeah. So later, I wish, hopefully today or Monday, I have time to go over using MATLAB program. How about I talk it now? Talk it about now. Okay. I don't need these sections, so then. And right now, this one is the manual solutions. And for higher order systems, for the multiple degree freedom systems, the MATLAB solution is this. And this can be useful and to double check for your calculations. What happened?
That was me.
Oh. Right now I'm very because right now I'm very focused on these things because the topic is very, very important. I don't want to screw up, rewind everything. Go back to the MATLAB here because for delivering the complicated concept and steps, the best way for instructor is do it at one time correctly. No rewinding. Okay, that would be good for students. So, okay, now we're back to MATLAB, and if you can solve for that one, we can do this here. Maybe you can open, say, homework 12 and .m. So that is kind of the file. Okay. In the file, you can input the M matrix. For this example is 10, 0. This representing you input the first row and use semicolon to separate row from rows. And the second row is 0, 1. And you separate the elements by a space or by a comma, either way. Okay. Then you input k equal to 35 minus 35 and minus 35 and 5. If you like, at the end of one statement, you can put a semicolon to suppress the display of the result on your screen. But really up to you, okay? And once you have done this one, then you're going to calculate using a single command. And that command is a very powerful tool. Eigenvalue, EIG. Okay. And for EIG, and that is the eigenvalue of the inverse n multiply with, sorry, I made a mistake here. The parameter shouldn't have the braces. You simply use mk And with this one, the MATLAB would know that is a matrix.
You can still declare this like that.
Yeah, yeah. So that's a declare. Yes.
It works if you have the brackets around it as well.
If you use the declare with this one,
It works.
it will.
Yeah.
In the old version, it seems not. But anyhow, let me stick with mine. And you use this command, okay? And that basically will give you, this will give the eigenvalue, which means omega squared, okay? So let me explain further. So this is a very powerful command, and one single line that solves for eigenvalue and eigenvectors problem. This single line basically replaces all the manual calculation from here to here. Okay, and the output, which means the production of this result, is very abundant. If you want to extract the eigenvectors and eigenvalues, listen this carefully. If you only type EIG, and you won't get too much, I guarantee. If you want to get everything you need, in this output here, you provide whatever you can use V and D. V is a parameter to store the result. D is another parameter to store result. And what is V? Here, let me make a note. For example, the output of V could be like this. 1, 5, 1, 2. You can see the output, the V is a matrix to store the eigenvectors result. First column is our vibration mode. The second column is another vibration mode. That'll be good? Right now I'm kind of doing the syntax explanations. Then the D is the matrix to store the result of eigenvalues. Okay, the eigenvalue is stored in the diagonal element. So that is 6 and 2.5. This is 0, not important. So this one, V, is to store the eigenvectors. Okay, so this is and this one is to store eigenvalue. Okay, the eigenvalue is stored in the diagonal element. The 0, 0 here, that's not important. And depends on the versions of the MATLAB, and sometimes the MATLAB won't give you in ascending or descending orders. I don't know why, and really depends on the subroutine of the MATLAB. Okay, subroutine depends on this command. So for this demonstration, I do it on purpose. Once you have this coming up, and you will have the two V and D coming up, look at the contents carefully. Okay, look at the contents of the V and D you get. Right now for this demonstration, you can see the first showing up is a 6, and that corresponding is our second natural frequencies. Then it corresponding, this is the first place, so that is the associated eigenvectors or vibration mode. This is the fundamental natural frequencies corresponding column 2, that will be his one. The MATLAB output will always match the given whatever the orders are from descending or ascending. They always place the corresponding eigenvectors with that particular the eigenvalues there. Will be good?
So that'll work with the 3x3? Just as
Also,
too?
3x3 also working as long as you change your M and K, the remaining will be the same. So for different problems, again, Kyle, right? For your question, if we have a 3x3, then you simply change the contents of M as a 3x3. Maybe later I can come up with another example here quickly.
Like 3 semicolon, 3 numbers, semicolon.
Yeah, give me a few minutes.
No.
Any questions so far?
No, my question was specifically with the modal vectors. How
Yes.
do you try and get the first term to 1? Like if you were going to have.
Yeah,
vector of
okay,
two
and
terms,
that will give you another 1.5 hours. I will come to there, okay? That's called the normalization. I will mention that one. Okay, we're back to here, and to this step, any questions? At least right now you have 2 approaches, right? Is that the answer? Wait a minute, no. That is a MATLAB output. Again, this MATLAB output gives us is the eigenvalues omega squared. So whatever the number got here, you simply write the additional line and take the square root, and that is the natural frequency. Okay? Maybe you can say if omega 1 equal to the SQRT and D 11 omega 2 equal to D11 and omega 1 equal to SQRT D22. The D11 meaning the 11 element of the matrix. This means the 22 elements of the D matrix. You simply take the square root. Okay. Questions?
That was it.
Okay, good. Then I can demonstrate, say, for example, 3 by 3. Okay, so say if we have a 3 by 3 matrix, something like this. So say M will be equal to say 1, 2, 3, 0, 0, 0, 0, 0, 0, and K will be something like say, let me make up one. 3, 5, 6, and minus 1, and minus 2, and minus 1, minus 1, something like this one, arbitrary. I don't know whether this is legible or not. So in this way, you simply, in your M matrix, you simply is 1, 0, 0, and 0, 2, 0, and 0, 0, 3. And K, the same thing, you simply input the corresponding numbers. And then, again, this topic from downward, from this portion, this will be the same. This will be the same for all the problems. Then the remaining post-process, you simply carefully do it. So maybe you can use
That'll be a lot easier, right?
You have to still learn how to do this.
Yeah, yeah.
Okay. I don't know. Yeah. Good?
Are
Yes.
you going to give us a 3 by